We had a webinar on well completion accessories by Mr. Manish Verma. We had a webinar on the importance of planning for startups in the oil and gas industry by Mr. Mandar Pathak. We had a webinar on data science. These are some of the posters of the events that we had in the past. We had our drilling and well engineering internship, Mind Marshal, data science course, personality development course, because we aim for a wholesome development of the students. GIS webinar, SolidWorks industrial software training, which will be hosted in the future. Why you should collaborate with us? We focus on overall development of students from technical to brand building. Top-tier faculty with active teaching experience at oil and gas companies, webinars on trending topics and in the industry, experience of the oil field right at your screen with the video facilitated teaching. The certificates and its authenticity, being a Government of India identified company, the certificates are highly valued. These are our technical advisors, Mr. Sanjay Joshi, experience of over 25 plus years, Mr. Milind Gokhale, experience of over 30 plus years, Mr. Vipin Bhalla, of experience over 30 plus years, Mr. Sameer Kale, an experience over 30 plus years, and Mr. Pulkit Goel, of experience over 14 plus years. So you can see that all our technical advisors are highly experienced in the industry. Thank you. So today, now I would like to welcome Women in Energy, Ms. Yogashri Pradhan ma'am. She is currently working as Senior Reservoir Engineering at Endeavour Energy Resources Limited Private. Over to you, ma'am.
Thank you so much for the kind introduction. I'll go ahead and share my screen to go on with the workshop. Excuse me, that is not the right screen. Let me just share my screen. Let's see, share screen. Okay. So good morning. Well, it's morning for me, but good evening for everyone. And for those of you in other parts of the world, good afternoon. I'm Yogashri Pradhan, and as stated in the introduction, I work as a reservoir engineer. The purpose of this 3-day workshop or this lecture series is really for those who don't have a background in reservoir engineering or who haven't taken the reservoir engineering classes yet. And I wanted to give you an introduction to some reservoir engineering concepts. The first thing
hi, Ms. Yogeshri. Sorry to interrupt. There is a voice lag.
Pardon?
There is a voice lag at your end.
Can you hear me now? The purpose of the 3-day workshop is to give yourself an introduction to reservoir engineering, and I strongly encourage that the resources that I do provide will be things that you will look into a little bit later on. Maybe there's some books that you can read in reservoir engineering, and I'll suggest some of them to you. Most of the texts that I'll cover for today will be directly from some reservoir engineering textbooks. The Craft and Hawkins textbook, for instance, the 3rd edition, is what's going to comprise of the majority of today's presentation. As an outline for today's presentation, I'll go over the types of reservoirs, the fluid type, your drive, the fluid and rock properties, material balance. Then I'll go over single-phase gas reservoirs, gas condensate reservoirs, and some of the best practices, undersaturated oil reservoirs, saturated oil reservoirs, some equations that are governed for the single-phase fluid flow, water influx, and I'll talk about history matching, specifically about decline curve analysis. But before I move on to the presentation, I want to give an introduction of what exactly is reservoir engineering. So let me start with
the ground area that contains oil and gas in the rock. Engineers help determine how much oil and gas is in a reservoir, how much can be recovered, and how quickly it can be produced. We also determine what types of wells should be drilled, how many are needed, and where they should be located. We work with reservoir models that are built using seismic data, well logs, production history, and other information. These models allow us to perform simulations that help us determine how to manage a reservoir. There are many options involved in reservoir management, so we perform economic evaluations of options to help our company make the best decisions. Finally, we prepare periodic estimates of remaining recoverable reserves. These estimates are relied upon both inside our company and by outside investors, so it's important that we get them right. My job is to design and oversee the drilling of.
So that's a general introduction of what a reservoir engineer does. Was everyone able to hear that? Was everyone able to hear that? I think I didn't share computer sound. So let me share my screen again. Let me share my screen again. And let me start over this presentation.
If you don't know, a reservoir is an underground oil and gas in the rock pores. Reservoir engineers help determine how much oil and gas is in a reservoir, how much can be recovered, and how quickly it can be produced. We also determine what types of wells should be drilled, how many are needed, and where they should be located. We work with reservoir models that are built using seismic data, well logs, production history, and other information. These models allow us to perform simulations that help us determine how to manage a reservoir. There are many options involved in reservoir management, so we perform economic evaluations
to help our company make the best decisions. Finally, we prepare periodic estimates of remaining recoverable reserves. These estimates are relied upon both inside our company and by outside investors, so it's important that we get them right. My job is to design and oversee the drilling of wells, so I'm called a drilling engineer. Drilling can be extremely complicated. We have to drill holes.
So I hope everyone was able to hear that. Let me go back to the presentation. First, I'll go over the types of fluids, as I mentioned before in reservoir engineering. There are 5 types of fluids. We're looking at a black oil, a volatile oil, a retrograde condensate, wet gas, and dry gas. And the way that you're able to figure out these different types of fluids are from your initial gas oil ratio, API, and the color of the stock tank liquid. So they're useful indicators. Now for the black oil, now I'll go into the detail of what each type of. Can everyone hear me? I'm going to take that as a yes. So for the black oil reservoir, you're starting with the liquid, or you're starting with the black oil from the reservoir. You're starting with the black oil and a liquid from the wellbore. And then when you reach the surface, you have some gas that's coming out of solutions. And you have some that are coming out of solution, but you still have a liquid that's coming to the surface as shown in the phase diagram over here. And at the separator, you're still reaching at a liquid phase. That's considered as a black oil reservoir. For a volatile oil, you still start out with the liquid in the reservoir. At the wellbore, you're reaching some percentage of gas. And then once you reach the separator, you have more gas that's coming out of solution. For a gas condensate reservoir, let me look at the chat again. For so for those who are telling me to chat or to speak in Hindi, I can't speak in Hindi very well. I only understand it very well. So I apologize if there's a language barrier. For the retrograde condensate, you're starting with the gas in the reservoir, And then you have some liquids coming out of the reservoir once you reach the wellbore. And then when you reach the separator, you still have more liquids coming out of the reservoir. That's considered as a gas condensate reservoir, where it's primarily a gas reservoir, but once you reach the surface, you have some liquids that are coming out. That means you're reaching the dew point of you reach below the dew point of the reservoir, and you're getting some liquids. Let's see. For the wet gas reservoir, you start out as a gas, and then as you reach the wellbore, you're still reaching at a gas phase, but once you reach the separator, you still have some liquids coming out of the gas phase. Because it's primarily a gas reservoir, but there's some liquids that are coming out, that is considered a gas reservoir, a wet gas reservoir. For the dry gas reservoir, you don't have any liquids coming out in any parts of the production phase. It starts out as a gas phase in the reservoir, it's still a gas phase at the wellbore, and then there are no liquids that come out of solution in the separator. I got most of this information from Phuket. I got most of this information from the Phuket website, so if you want to look for more information there, you can. Let's see, next slide. Here are a couple more slides that I've gotten from the Craft and Hawkins book, and then the Walsh and Lake book, the reservoir textbooks. I would suggest you get these textbooks to get more information or to give yourself more knowledge in reservoir engineering. From the Craft and Hawkins textbook, okay, my screen stopped sharing. Let me share my screen again. From the Craft and Hawkins textbook, you have different component breakdowns for each of the 5 types of fluids. If you look at the component breakdowns, you have lighter components mostly coming from your black oil, from the black oil, but you mostly have heavy components coming from your black oil. And then for each subsequent fluid type, you have much higher, lighter components. If you look at the stock tank gravity, as you go to the lighter fluids, you're getting higher gas oil ratios. And for the API stock tank gravity, you're getting higher API gravities as you reach along the different types of fluids. And then this gives you the different types of colors for each fluid type. So for a black oil reservoir, you're getting a greenish black. For a volatile reservoir, you're looking at medium orange. A gas condensate reservoir is a light straw color, and for a dry gas reservoir, you're looking at water white. And same goes for wet gas. This chart on the right from the Walsh and Lake textbook gives you an idea of what to look for when you're looking at heavy oils, conventional black crude oils. This gives you a better breakdown of the different types of fluids. So black oils can be split up into heavy oil, conventional black crude oil, and then high shrinkage crude oil, so a little bit higher in API gravity, or they're a little bit lighter compared to the other types of black oils. Okay, next slide. Now I'll cover the reservoir drive mechanisms as a basic overview in engineering. To give you the overview of drive mechanisms, you're looking at an energy compression of water and rock, oil and gas. Water is contiguous to and in communication with the reservoir, and gravitational energy causing oil and gas to segregate. So this chart over here gives you an idea of how the drive mechanisms are separated. We're looking at 3 types of drive, such as expansion drive, water drive, and compaction drive. My screen stopped sharing. So let me go ahead and share my screen again. Let me go ahead. So the host has disabled participant screen sharing. Can I get my permissions to screen share? The host has disabled me from screen sharing. Can I get a I'm still not getting permissions to screen share. Okay, now I have permissions to screen share. Great. Then you have oil drive and gas drive, and then for water drive, you have partial and full. For the gas drive, you have other types of drives, such as solution gas drive, gas cap drive, and then gas drive. And then for the gas cap drive, you have segregating or non-segregating based on gravity. Expansion drive, it is the expansion of reservoir fluid influencing reservoir production. So you have oil expansion and you have gas expansion. I talked about solution gas cap and general gas drive. Solution gas is dissolved gas influences reservoir production. You have gas cap drive, which is gas expansion from a gas cap, which influences reservoir production. And you have a general gas drive. For water drive, you have partial water drive, which means an aquifer has poor water quality and will diminish. And for a full water drive, you have a stronger aquifer, and that influences reservoir production. For compaction drive, you have pore volume contraction that contributes to the reservoir production. For rock properties, I listed some equations down here that could be very important in reservoir engineering. For example, you're looking at porosity. Porosity is, the simple concept of porosity is really your pore volume divided by your bulk volume. So think about a Swiss cheese cube and think about all the holes in the Swiss cheese. The holes in the Swiss cheese divided by the total volume of the Swiss cheese is going to be your porosity. Then you have isothermal compressibility. So the same temperature and you have compressibility, which is your 1 over volume times the change over volume with respect to pressure. And these are your relations of your compressibility with respect to porosity. And the first equation for your compressibility was developed for sandstones with the porosities ranging from 2% to 23%. For the compressibility relation, the second one, that's developed for limestones with the porosity ranges of 2% to 33%. Then you have fluid saturations of oil, water, and gas, which are going to be pretty important for your rock properties. And to give you an example of what exactly saturation means, it's pretty much the percentage of fill-up that is within your porosity that constitutes of a certain fluid. So for example, your oil saturation would be the porosity that is filled by oil divided by the total porosity. For fluid properties for gas, you're looking at an ideal gas law. That is one concept that I would say that is pretty important. Then you have so it's PV equals nRT, where P is your pressure, V is your volume, N is the number of moles, R is a gas constant, and T is your pressure, or T is your temperature, your absolute temperature. You have specific gravity here, which means your density of gas divided by the density of air, which is your molecular weight divided by the molecular weight of air, right below. Then you have your real gas law, which is your PV equals Z nRT, and Z is actually your compressibility factor for your real gases. Z is defined over here, where your actual volume of N moles of gas at the temperature and pressure divided by the ideal volume of N moles of gas at temperature and pressure. You have your formation volume gas factor, which is your Z nRT over P, which is your formation volume factor is pretty much what is the factor that it takes to take from the reservoir to the surface to get your volumes at the surface. And you have your gas compressibility, which is your 1 over P minus your 1 over your compressibility factor with respect to the change of compressibility factor, and that's with respect to the pressure. So I wanted to give you a sample problem to help you figure out how to determine your Z factor. You're going to learn how to get your pseudo-critical pressures and your pseudo-reduced pressures and your pseudo-reduced temperatures with respect to different types of gases. Here, these are relations with the specific gravity of gas. So you take your specific gravity of gas and you figure out your relations to the pseudocritical pressure, and you take your pseudocritical temperature. And so these are called sentence correlations with respect to with respect to certain gas densities. So using a certain specific gas gravity of this range, so 0.554 to 1.8, you could use these correlations. And if you have a larger range for condensate gases here, then you use these. Then you use this formulation for your pseudo-reduced pressure and your pseudo-reduced temperature. For your pseudo-reduced pressure, you go to the graph on the right here. So your x-axis is your pseudo-reduced pressure, your y-axis is your compressibility factor, and these lines represent your pseudo-reduced temperature. So you take your pseudo-reduced pressure, you find the line of your pseudo-reduced temperature, and that's how you figure out your gas compressibility factor, or your Z factor. Now I'll talk about the fluid properties of oil. So you have your solution gas oil ratio, or how much gas is in solution when it's at the reservoir. Then you have your API gravity, which is another relation to the specific gravity of your oil. So it's another measurement. So you have 141.5 divided by your specific gravity of oil minus 131.5. Then you have your formation volume factor, which is your BO. You have one that is above your bubble point pressure. Your formation volume factor of oil is your formation volume factor of oil at the bubble point times the exponent of, or e to the power of your compressibility of oil, and then the difference between your bubble point pressure and then your reservoir, and then your pressure of interest. And then you have the pressure below the bubble point pressure. You have your BO times, which is equal to the density of the oil at standard conditions, plus this relation that includes your solution gas oil ratio times your specific gravity of gas at surface conditions, and you have, and then you have your density of oil at the condition of below your bubble point pressure. You have oil compressibility here. So your compressibility of oil is your 1 over volume with respect to the changes in volume from start to finish. And then you have your pressure differences from start to finish. And viscosity is very important. So viscosity can be measured in centipoise, or it can be measured in Pascal seconds in scientific units and SI units. So your viscosity is going to be an important fluid property, because you get to figure out how viscous your fluid is, or how easy it is for your fluid to flow in the reservoir. Now I'll talk about the fluid properties of water. Water is a pretty simple fluid in how it's treated when it comes to reservoir engineering. You have your formation volume factor of water, which is typically 1, but it can range from like 1.02 or 1.05. You have your solution gas water ratio, which is true for which can be true for predominantly water-producing reservoirs. Excuse me. Then you have your isothermal compressibility, which is the change, which is your 1 over your formation volume factor of water times the change in your formation volume factor of water with respect to pressure, and then with respect to temperature, with respect to the same temperature. And then your viscosity of water, which is typically 1 centipoise. I'll now go over the material balance portion of the presentation. Material balance is pretty much a conservation of mass kind of equation, where in plus out is equal to in plus out. Over here, it's your oil expansion plus your gas expansion plus your formation water expansion plus your water influx is equal to your oil production plus your water production. And this is the formulation of your material balance below. So this is your oil expansion, and this is your gas expansion term. This is your formation water expansion term, and this is your water influx. And this is equal to your oil production, and this is equal to your water production. If you're wondering what M is equal to the total gas in place times your formation volume factor of gas divided by your total oil in place times your formation volume factor of oil.
Hello?
Yes.
Ma'am, we have a doubt from one of the students, from Muru Vikra Marante. Viscosity measurements mm square upon second to Cp to Pa dot S dot. Please share unit conversion.
So are you talking about viscosity?
Viscosity measurements, yeah.
Yeah, it's Pa times second, times sec, so Pa times S.
Okay.
So here are some uses and limitations for material balance. For uses, you're determining the initial hydrocarbon in place, you're calculating your water influx, and you're predicting your reservoir pressures. For limitations, you have precision of values that relies on the data available. As the pressure declines, there is supersaturation, underestimating the average reservoir pressures. It's assumed that PBT gas liberation closely duplicates the same process in the reservoir in the well and separators, and that can actually vary widely, so that's causing error. The determination of average reservoir pressures in low permeability reservoirs, and uncertainties of free gas volume to the initial reservoir oil volume. That's going to be some of the limitations for material balance. For single-phase gas, you're looking at some important terms such as your original gas in place, which is the amount of acres per foot, and time, which is the amount of acres per foot squared, or in a conversion of acres to feet squared, and times your porosity. And you have your 1 minus your water saturation divided by your formation volume factor of gas. For the gas material balance, you're looking at your gas expansion plus your water influx is equal to your gas production plus your water production. And then assuming no water encroachment or water production, the material balance can be simplified to the gas expansion is equal to the gas produced. This can also be rearranged and reduced to your P over Z, which is equal to your initial P, initial pressure, divided by your initial gas compressibility factor times your gas in place, times your gas produced, plus your initial pressure divided by your initial compressibility factor. And here's a chart over here that gives you your P over Z plot and then your cumulative production. Reaching the end of the plot to get your x-intercept represents your initial gas in place. If you have a water drive, you're going to be coning upward. If you have some water encroachment when it comes to your gas production, which can make it hard to predict your original gas in place, so material balance is very important there. And then you have your volumetric gas produced times your P over Z. And you could have some water encroachments to where your initial gas in place could be a little bit higher in that curve. So here's the material balance in water drive reservoirs. Here are some important equations that are over here, where your initial volume is equal to your final gas compressibility factor times your temperature times your initial pressure, divided by your final pressure times your initial compressibility factor times your temperature, minus 1. And that's equal to the Z factor, your compressibility factor times your temperature, times the pressure at standard conditions, times your produced gas divided by your final pressure times your temperature at standard conditions. Then you have your water, plus your water produced minus your water influx. And it's referring to this curve on this plot over here. So a gas equivalent of the produced condensate in reservoir, gas equivalent is equal to the volume, and it's equal to your number of moles times your gas constant times your pressure divided by your pressure at standard conditions is equal to this term over here, and this is your estimation times your specific gravity divided by your molecular weight. And then assuming standard, and this is all assuming standard atmospheric conditions. So we have 60 degrees. And the temperature that is used over here is in Rankine. So Rankine is your degrees in Fahrenheit plus 460. And I apologize, I realize that this is all in oil field units and most of you are used to the metric system. So you may have to think about what is the metric equivalent for a lot of these terms. And then you have 14.7 psia and your gas constant is 10.73. Here is a visual giving you the significance of a gas equivalent of produced condensate and water. You have your well fluid that's going to the primary separator, and then you have a secondary separator, and then you have a stock tank. You have gas condensate that's being produced. You have gas that's being produced in one area, and then you have oil being produced in another area. For a two-stage separator system, you have a primary and a secondary separator, and you have gas produced in one area, and then you have condensate produced in another area. Excuse me. Whenever you have oil that's producing from a gas reservoir, that's considered a condensate. For gas condensate reservoirs, this is just to give you a visual here on where you can find gas condensate reservoirs. As you go deeper in depth, as you go deeper in thousands of feet, for some onshore plays in the United States, you find a lot of gas condensate reservoirs in this area where you have some really high gas to oil ratios in the reservoir. And here are a number of discoveries per 1,000 foot interval where your gas condensate reservoirs are coming from deeper intervals here. So this is just to give you an idea that you can find gas condensate reservoirs at deeper depths of onshore plays in the United States. Here's a workflow for determining the number of the condensate from your gas condensate reservoir. You first need to calculate your initial gas in place per acre foot. You need to divide the daily separator gas by separator oil. You need to calculate your initial gas fraction. Then you need to calculate initial gas and initial oil in place from the initial gas fraction and daily separator gas oil ratio. And the recovery strategy here is you have to use pressure as a maintenance, use gas as a pressure maintenance and a displacement fluid. Here's an overview of your gas condensate reservoir showing you at different pressures. You have different elements you have different values of elements at different pressures. And you have different compositions at different pressures too, which makes your gas condensate reservoir very sensitive to pressure. You have heavier elements that are going a little bit upward as the pressure goes higher, and your lighter elements stay relatively the same. So your C1s, C2s, and C3s. So your methane, ethane, and propane stay relatively the same, but then when you reach your butane, pentane, your hexane, and then your heptane pluses, you're seeing some curvature as the pressure changes. That becomes a little bit more sensitive, your heavier elements. So here's some best practices for volumetrics in gas condensate reservoirs. You duplicate reservoir depletion by lab studies on a representative sample on an initial single-phase reservoir fluid. You want to hold the sample at high pressure in the cell at reservoir pressure and initial temperature. And during depletion, the cell volume is held constant to duplicate a volumetric reservoir and therefore remove the gas phase hydrocarbon from the cell. Other notes to consider is that the oil phase is immobile until 10 to 20% saturation is reached. So at higher pressures than what you probably reach your higher oil saturations. For undersaturated oil reservoirs, here's the equation for your original oil in place for your barrels of oil, and then your material balance. You're looking at your oil expansion is equal to your oil production. And that's reduced to if you have the same solution gas oil ratio in an undersaturated oil reservoir, then you can reduce your material balance to your oil expansion is equal to your oil production. And here you can determine what your recovery factor is. So your produced divided your oil in place is equal to your difference in your oil, your total formation volume factor divided by the total formation volume factor. And if you're comparing at some time below the bubble point, this is the relation for the recovery factor here. You have to include the solution gas oil ratio at a certain pressure because you have some pressure below the bubble point. Here's some fluid sample information from undersaturated oil reservoirs. You have the solution involved GOR and liquid phase volumes. You have formation volume factors, oil gravities, and separator stock tank GORs for various separator pressures. You have bubble point pressure of the reservoir fluid, you have a compressibility of a saturated oil, and then you have a viscosity of reservoir oil as a function of pressure. And then you have fractional analysis of the casing head sample and of the saturated reservoir fluid. Here are some plots of your undersaturated oil reservoirs, just to give you an idea of differential liberation that you end up getting from your undersaturated oil reservoirs, where you stay at the same solution gas-oil ratio at certain pressures, and then when you hit the bubble point pressure, you are starting to get some gas that's going to come out of solution, and your solution GOR also declines, but your oil formation volume factor increases. Or actually, excuse me, it declines. Here you have your reservoir pressure and your recovery in percentage. Once you hit the bubble point, your recovery factor ends up increasing a little bit more. And then as you decline in your reservoir pressure, you have the steeper slope. In saturated oil reservoirs, that includes liquid and gas present in the reservoir. Factors affecting overall recovery is large gas caps, continuous uniform formations, and good gravitational segregation characteristics such as Pradhan structure, low oil viscosity, large permeability, and low oil velocities. Here's the material balance for a saturated oil reservoir, so you have to include gas expansion as the material balance term, and you're also using your water expansion too. Or you're also including water influx, excuse me. And then you're using your whole gas production, your oil production, which includes your solution gas-oil ratio differences, and then your water production here. However, coordinate water and formation compressibilities are negligible when it comes to saturated reservoirs. So that's reducing your equation to just your gas expansion plus your oil expansion plus your water influx, equaling to your your oil and gas production plus your water production. I wanted to give you some clarification of terms. I did mention differential liberation before. So here are some definitions. So flash versus differential liberation, they're critical to understand the process, especially for fluids with a large percentage of intermediate carbon, hydrocarbons. So that's included for saturated reservoirs, such as volatile oil reservoirs. So intermediate hydrocarbons represent your C3, your C4, and your C5, your propane, your butane, and your pentane. Flash liberation means that all the gas evolved during a reduction in pressure remains in contact and equilibrium with the liquid phase from which it's liberated. Differential means the gas evolved during a pressure reduction that's removed from the liquid as rapidly as is liberated. A little bit of information in volatile oil. It's intermediate in volatility between a moderately volatile reservoir and a gas condensate reservoir. And you have large portions of ethane through decade at a reservoir temperature at 250 degrees Fahrenheit or above. And traditional PVT sampling is not appropriate for this type of fluid because, again, it becomes a fluid at the reservoir, but once you reach the wellbore, you see more gas that's coming out of solution. At a single phase flow, I'll go over this. There's a lot of information for this actually. I'll now go over the single phase flow portion of the presentation. So here's some definitions when I talk about steady state, pseudo-steady state, or unsteady state. For steady state flow, that's a condition under which a pressure at any point in the reservoir remains constant over time. For pseudo-steady state flow, it's boundary-dominated flow. This occurs when the drainage radius reaches the reservoir boundaries once the transient period ends. And then for unsteady state flow or transient flow, these are flow parameters, i.e. the velocity and pressure. They're dependent not only on the position, but also on time. An incompressible fluid is typically water. When we talk about slightly compressible fluid, we're typically talking about oil. And then for compressible fluids, when I'm going to talk about the equations, they're typically gas. For a single phase flow, and I'll go over Darcy's law. Darcy's law is pretty much the fundamentals when it comes to a single phase fluid flow in reservoir engineering. So for Darcy's law, you're looking at the conversion from SI units to the oil flow units with this term times the permeability times your cross-sectional area times your pressure differences, all divided by your total formation or your oil formation volume factor times the viscosity and times the length at which you are flowing your fluid. So this is your L. That one on the chart on the right. Darcy's law for gas or compressible fluids. So in steady state is going to be this relation right here. And your M is your pretty much you're taking into account pseudo pressures, because you have some differences in your volumes when it comes to gas at different pressures. So this is the integral of your reservoir pressure to your pressure of interest, and then with respect to your pressure of interest over your viscosity times your compressibility factor at your reservoir pressure and at the pressure of interest. Assumptions for Darcy's law is that you have laminar flow, steady state, homogeneous, and your total cross-sectional areas is considered. So that's your chart on the right over here, or your picture on the right over here, where you have your total cross-sectional area, you have your section of interest, and then you have your P1, your pressure of interest at one area, and your P2, your pressure of interest at your other area. Excuse me. Another more concepts to single phase flow is that you're looking at permeability averaging. Permeability averaging laterally is in series, so that's your summation of your lengths divided by your summation of your lengths divided by your permeability. Permeability averaging vertically, it's your perm times your height or your thickness summation divided by your total thickness. And then your permeability flow through your capillaries and fractures, you have your relation over here. For radial flow for incompressible fluids, you have this relation, which is your conversion to your SI units to your oil field units, times your external pressure difference between your external pressure and your well bore pressure, times your permeability and your thickness, divided by your viscosity, your oil formation volume factor, with the natural log to your external radius divided by your well bore radius. Then for the radial flow for slightly compressible fluids, you have your same relation that's over here, and then you only take into account the compressibility. I do want to point out that this W represents your width in fractures, and your AC represents your contacted area. For radial flow and compressible fluids, so for your gas, you're looking into your pseudo pressures again, and then your permeability times your height. And then for your permeability average, radially, I've heard that I'm echoing a lot. For your permeability average radially, you're looking at your perm average times your Ka times your Ke. So you have your Ka times your Ke, so at different thicknesses, times your natural log of your external radius divided by your well bore radius. So this is your external radius, and this is your well bore radius, if you look at the bottom right. And then you have your Ka, which is here, times your logarithm of your external radius, divided by your well bore radius plus your Ke, so your Ke is here, times your logarithm of your RA radius divided by your RW radius. So for single phase flow, you're looking at the mass entering of the volume element during the time. So now I'll talk more about the diffusivity equation, where your mass entering the volume element during your certain time delta t minus your mass leaving the volume element during interval delta t, that's equal to the change in the mass volume element during the interval delta t. And this is going to be a breakdown of your diffusivity equation, where your permeability divided by your viscosity times your density and times your radius with respect to the change of your pressure divided with respect to the change in your radius. That's and that's equal to the density times your porosity times your compressibility of your fluid times your change in your Okay, now I'm unmuted. I wasn't allowed to be unmuted before. So that's equal to the porosity times your change in pressure with respect to your change in time. And I'm not going to go into every single detail here. If you want to take a screenshot of this, please do so. But this gives you the derivation of your diffusivity equation in your Kraft and Hawkins textbook, where you start out with the mass entering the volume element, the mass leaving the volume element, the change in mass element during the interval delta time, and then you write down this equation, and you start reducing the equation by dividing common terms and take the limit to 0. And then this is what you end up getting for once you take the limit to 0, and this is when it's reduced. And then you have Darcy's, then you introduce Darcy's equation for fluid flow in here. And then you realize, then the minus sign can be dropped from the Darcy's equation. And then the porosity from the partial derivative term on the right-hand side is eliminated. Then it can be shown that porosity related to the formation compressibility is here. You apply the chain rule for differentiation, and then you substitute that equation to get what I showed you before for the diffusivity equation. For radial flow, slightly compressible fluids, for transient flow, you have your initial reservoir pressure minus this relation here for your fluid flow, your viscosity, and your formation volume factor divided by your KH. And that's equal to the exponential integral and your in your porosity, your viscosity, your total compressibility, and then your R squared divided by your permeability times your time. Radial flow for your transient, you're taking into account your pseudo pressures here again. For slightly compressible fluids, for pseudo steady state flow, you're taking into account your shape factors here. That's what CA is equal to, and then your contacted area. And then for radial flow, for compressible and pseudo steady state flows, you're still taking into account your pseudo pressures here, and then you're taking into account your temperature at standard conditions and your pressure at standard conditions too. I also wanted to talk about the productivity index, which is your Q divided by your P minus PWF, so your reservoir pressure minus your wellbore pressure, and then here's your superposition, or your total pressure drop is going to be your it's going to be your different pressure drops using this equation here. For water influx, it's the rate of active volumetric voidage plus the rate of free gas volumetric voidage plus the rate of water volumetric voidage. And that is your relation that's shown over here. So that is your active volumetric voidage, gas volumetric voidage, free gas, and then your rate of water volumetric voidage. For unsteady state models, you're looking at the Edgewater model, which is your water influx enters the formation from flanks with negligible vertical direction, and this is the relation that you're looking at here. And your bottom drive is you have significant vertical flow, which you're introducing a Z term over here, which is a similar setup as this one, but you're introducing a Z term here. And this is what your Z is equal to. And now the last part I'll talk about is your decline curve analysis. Decline curve analysis is an empirical way to fit your production data, and that's very important for reservoir engineers. The general equation for your decline curve analysis is your 1 over your rate with respect to your change in rate over time, and that is equal to your curvature factor times your rate to the power of your decline. Here's the equation for your exponential decline with your B factor equal to 0, and that's your rate is equal to your initial rate times your exponent minus your e to the minus your time times your initial decline. For cumulative production, you're looking at your Q1 minus your Q2 divided by your initial decline, or divided by your decline. For your hyperbolic decline, you're looking at a curvature or your B factor between 0 to 1, and then this is your relation for your hyperbolic decline. For cumulative production, you have this relation for your hyperbolic decline, if you can see my cursor. For harmonic decline, your B is equal to 1, so that actually simplifies the hyperbolic equation to this equation, where it's your Q naught, your initial rate divided by your 1 plus D initial decline times time. And this is what your cumulative production looks like if you were to integrate this equation with respect to time. I'll now talk about the modified hyperbolic decline. You'd be a hyperbolic when your decline is greater than the terminal decline rate, so the hyperbolic decline rate is used. When your D is equal to your terminal decline, so once you reach a certain terminal decline, then you start using an exponential. So that's why you use your modified hyperbolic decline. This is used to model linear flow and boundary dominated flow in a reservoir, and that's typically used for unconventional horizontal producing wells. So that's typically used whenever we're using our decline curve analysis. We don't just strictly use hyperbolic, or we don't just strictly use your exponential. You use a combination of both by agreeing what your terminal decline is going to be. To give you some pointers on what type of decline we're talking about, sometimes some DCA softwares talk about nominal decline, some DCA softwares talk about effective decline, and this is just to give you an idea of what exactly a nominal and effective decline is. When we're talking about nominal decline, we're talking about the slope tangents to the data point, and when we're talking about an effective decline, we're talking about the slope not tangent to the data point, so it's more of a secant when you look at this. So some limitations for decline curve analysis is that the assumption of a constant flowing bottom hole pressure throughout the life of the well. A conservative choke management strategy will result in shallow declines, which could delay in production forecasting or hinder the certainty of time rate analysis results. That comes from a Texas A&M paper from 2014. And then the exponential decline curve trends to underestimate reserves and production rates. The harmonic decline curve has a tendency to overpredict the reservoir performance. So exponential can underestimate, and then harmonic can overestimate. And the production decline does not follow any other model, and they could cross over an entire set of curves. So that's in some cases. And this comes from a Stanford University study back in 2003. So that concludes my portion of the workshop covering the fundamentals of reservoir engineering. And I know I went a little bit over time, but I am open for a few questions. Does anyone have any questions for me? Petra Booster, I'm going to hand it back to you. I don't think anyone has any questions for me. Oh, Rushali, I'll hand it back to you because I don't think anyone has any questions for me.
Good evening, ma'am. Actually, they are asking for me to unmute themselves. Just wait for a second. I'll check if somebody has any query. I'll read it to you. Is that okay?
Yeah, that'll work. How does the decline get affected when we do water injection by a sweeping versus pressure maintenance into the aquifer instead of injecting into the oil reservoir? That is a great question. How does the decline get affected when we do water injection by a sweeping? It really depends on your reservoir. So if you have a consolidated reservoir where you have equal grain distributions and you have really good, and if you have really good sweep efficiency, I would say that you'd get a better, so it also depends on what time of the life it is. Water flooding is what I'll talk about tomorrow. That's going to be your secondary recovery. And then you have aquifer that's injecting into the oil reservoir. I would say that the aquifer that gets injected into the oil reservoir would be a better recovery because you're recovering a lot more because that's during your primary recovery portion of the reservoir. And then you have your, as opposed to your water injection sweeping. Now, it really just depends on your reservoir, and it depends on the quality of your aquifer too. I did mention recovery increase after bubble point pressure. Now let me show you my slide. And for those of you who want to ask any more questions and connect with me, feel free to connect with me on these platforms over here. You're getting more gas that's coming out of solution. That's one. Let's see. You're getting more gas that's coming out of solution. That would definitely be one. And according to the field, yeah, you're getting more gas that's coming out of solution, so you just have a higher solution gas drive. I would say that's the reason why. Any other questions? When to use flash vaporization and differential vaporization? The conditions of applicability, how do they vary with time during these tests? It's better to take these tests during the early time of the production life, because if you take this during the later time of the production life for both of your tests, then chances are you're going to get two phases already for your well, so you wouldn't get an accurate representation for your flash vaporization and your differential liberation tests. In undersaturated, is it preferable to fall below the bubble? Okay, there's a lot of questions here. Let me go one by one. Okay. When to use, what are the conditions of applicability with oil formation in solutions you are? The applicability, again, is to use it during the earlier time of the well life. Use differential liberation if you want to use flash vaporization if you, so flash vaporization is if you don't want to remove any gas that's coming out of the reservoir, and your differential liberation is you want to use that when you want to remove gas, when you want to remove your gas. But you could use either one. But I would say that you have to take these tests during the early life of the well. How is solution of the gas calculation? Density of the gas. If you want to see the density of the gas calculation, I'll share my screen. I'm not sure what you're asking, but for your single phase gas, let's see. This is your specific gravity. So this is your specific gravity. And this is your density of your gas calculation. And then your rock properties, your saturation of the gas is going to be your porosity that's filled by gas divided by your total porosity. And then throughout the field development, are we updating the material balance through the water cut meters and separator tests, or is MB just a one-time thing? You can do this throughout the field development. I understand in undersaturated reservoirs, in undersaturated reservoirs, is it preferred to fall below the bubble point? It may increase recovery factor, may also bring concern to produce gas. In conventional reservoirs, that is true, that if you are reaching your gas already, then you're probably, then depending on your relative permeability, that could be a concern. In unconventional reservoirs, you will be reaching below your bubble point anyway. And I'm getting messages that the audio was not clear. It's too much echo. I don't know what to do with that. Is this better? In undersaturated reservoirs, audio is now clear to us. That's great. So it may be a concern for conventional reservoirs, but for unconventional reservoirs, you're eventually going to be reaching the end of bubble, or reaching below bubble point anyway, so you just have to keep reducing. Like, there's nothing you can do about it. You're eventually going to reach your bubble point anyway. How do you find vertical permeability, or KV over KH? Well, it depends on your formation that you're looking at. In unconventional reservoirs, your KV over KH is going to be a ratio of 0.1. So once you know the horizontal permeability, you can calculate your vertical permeability. Now, in vertical permeability for your conventional reservoirs, you'd have to take a core, and then you'd have to do some permeability tests for your vertical permeability and your horizontal permeability. Are there any other questions? Thank you so much, Syed. Let me know if there are any other questions. Again, if you have any other questions, feel free to reach out to me. I'll leave this up here. Feel free to reach out to me here. I have one more in the chat box. Should a reservoir engineer be well versed in geology, or is the work of a geologist to make the reservoir model with all the upscaling done? A reservoir engineer should be well versed in geology. You need to know some background in geology to understand where exactly to land your wells and to understand the heterogeneity. And you need to have a basic background in your geology. It will make you a better reservoir engineer. And is the work of a geologist to make the reservoir model with all the upscaling done? That is the work of a geologist to make the reservoir model, but the reservoir engineer and the geologist must communicate with each other to create the accurate model. Any other questions? I don't think there are any more questions, are there? Petra Booster, I'm going to hand it over to you.
Hello. Thank you, ma'am. I think there are no further questions from the participants. It was a lovely experience and a great session. It was very informative and very insightful. Looking forward to tomorrow's session as well, which will take place during the same time period. That is 7:30 to 8:30 Indian Standard Time.
Awesome. Well, thank you for having me, and I'm looking forward to tomorrow.
Yes, ma'am. Thank you, ma'am.
All right, take care.
Thank you, everyone, for attending the workshop. Tomorrow's session will take place through the same link and during the same time period. So please be there on time. Tomorrow we will start at 7:30 sharp with ma'am explaining the further content of her workshop. Thank you, ma'am.
Thank you.